So in this lesson, we're going to extend what we learned in the previous lessons when we talked about atmospheric detonations and the pressure waves created by them and the damage caused by those pressure waves. And we're going to look at what happens if we have our detonation very near, kind of at or below the surface of the ground. In the next lesson, we're going to look at what happens when that occurs underwater. So to start, we're going to look at a photograph that was taken from inside an underground chamber created by a nuclear detonation, specifically by a 3 kiloton device. Now this crater's about 20 feet high and about 50 feet in diameter, or sorry, meters, 20 meters high, 20 meters in diameter. And we've got this cool little figure here, and then we have the actual photograph. Now there's this line that says rubble pile, and it's really hard to make out in this flat, two-dimensional, very confusing looking photograph, but so I've kind of drawn where the rubble line is in this red dotted line. Okay, and there's a couple of things in here that we should notice. So for one, that rubble pile, that rubble line, this is caused by material that has been created and fractured and broken up as our pressure, our expanding pressure from our nuclear device has occurred. Now, if it's, it expands spherically, so all of that stuff, material underneath where the detonation point occurred, it doesn't really go anywhere. It just stays where it was, where it was created or where it was broken or pushed out of the way or whatever. All the stuff that happened above an imaginary horizon line, because we've subjected it to these enormous pressures, it doesn't really have any structural stability anymore. And then once that pressure has subsided, the material that's been broken and is barely hanging on, it will end up falling down from the upper part of the chamber that we've now created. And this is what creates this little rubble pile. The second thing is we have a line here that says water level produced or introduced by post-shot surface drill holes. Now, in order to get some relevant information that they would need to fully characterize the device that they've just tested, sometimes the testers will drill holes down into the underground crater or the underground void that we've created so that they can extract material or take pictures such as we see here to help them with whatever it is that they were looking for. When you drill holes for stuff to get out, obviously stuff can get in, and water is one of those things that gets in. So water finds its way down through these holes that are drilled, and then will, until those holes are plugged, will fill up to a certain portion of that rubble pile that we have, that we see in both this diagram and the picture. Now, I would imagine if the water table was high enough, then something like this could get completely filled by water and basically become an underwater void within the ground. So a water-filled void. Imagine doing it somewhere like Florida where the water table is several inches above the ground. I suspect that something like that would happen. But here, in a place like Nevada, water table is very low. And so we're not seeing a whole lot of water coming in, but some of it does. And the reason that we know that is from the samples that they took when they drilled these holes. And then finally, we have approximate upper boundary of melt. And this is, okay, so as our detonation occurs, we're expanding, we're hot, high pressure. So first we're going to do a lot of ionization like we would do in the atmosphere as our fireball expands. But that's not going to last all that long. And then what's going to happen is as we lose energy, we stop ionizing and we just start melting. Okay, the material. And then outside of that, as we move outward, then we're fracturing the material. And as we move out, we're doing that deformation. We'll see that here in 1 second. So that approximate upper boundary of the melt is kind of where the pool of melted material would have collected at the bottom of this chamber that we've created. Now, when we get this pressure wave, it's very much like we get in the atmosphere, okay? So we're pushing out in all directions, and it's a singular wave. It's a singular pulse-type wave that's a longitudinal transmission, what basically means radially away from the point of detonation. And this is what we see here with this top figure. Now, another way that the Earth can move is something called an S wave or shear wave. And this happens when we have a large displacement of Earth in a given direction or dimension, like in the y-axis, the x-axis, or the z-axis. Now, when this happens, basically it's like having a slinky, right? If you stretch out a slinky and you take part of it and pull it down and then let it go, and then it goes up and down, and you basically get what looks like a traveling wave, that's a shear wave. Okay, when we have earthquakes, a lot of earthquakes are caused by displacement of the ground in some method or in some way, and this produces these shear waves. Now, interestingly enough, because our nuclear detonation is basically a point source expansion, right? It's not displacing Earth in any one dimension. It's just pushing everything outward. So all we really see is that pressure, that primary or P wave moving out. And we can see this in these two different seismometer readings that we have from the Nevada test site. The top being an earthquake that occurred, and the bottom being a nuclear detonation. So what we can see here is we have our P wave, pretty high amplitude P wave that occurs. However, what we see is a little bit later, we see another high amplitude wave, and this would be the associated S wave or shear wave. If we look at the red one, which is a nuclear detonation, however, we see that all we really have is a P wave. We have a very extremely low amplitude, if any amplitude, associated shear wave that goes with it. So this is by one of those primary methods of determining whether or not something that's detected by an organization like the Comprehensive Test Ban Treaty Organization, or CTBTO. If they want to know if something was an earthquake or a nuclear detonation, they can look at the readings coming out of the seismometer and say, is there the presence of any secondary or shear waves? If there is, it's definitely an earthquake. If there's not, it may be something else, including a possible nuclear detonation. Now, I'm not going to get too much further into it. There have been events that were not nuclear detonations that very much looked like that on the seismometer, but they're very rare, few and far between. So what happens when we're not super deep so that we create a cavity that just sits there, right? Part of the cavity collapses, but not a whole lot. What happens if we're close enough to the surface of the ground to where we can actually have an effect? Well, this is sort of a moderately buried device, depending on its yield. Of course, that will change. Wherein what we end up doing, so we'll look at this figure here. We have our solid puddle. It says radioactive glass. It's basically whatever the material that the ground is that we melted. Since a lot of ground materials have high levels of silicon in it, you melt silicon, you get glass, hence the radioactive glass. And it's radioactive because it's trapped a lot of the material, a lot of the radioactive debris, fission fragments and such from the weapon. They settle into it as it's still in a molten state, and it traps it in there, and it becomes radioactive glass. So what we see here is as the device expands, as the pressure moves outward, it primarily wants to move upward because of pressure equalization. The gases want to escape any way they can. So gases are lighter than surrounding atmosphere. They want to move upwards. That's kind of what this is showing, but it's not necessarily always the case. So what we see here is that fractured zone. This is where we've that pressure wave that we've created. It goes, as it moves outward, it fractures a lot of the material that it travels through. So it becomes basically rubble that's momentarily held in place. Right? It's being forced in place by that outgoing pressure and those gases that are trying to escape. However, as soon as that pressure subsides, what's going to happen is all of that fractured material, which isn't connected really to any of the ground around it, it's going to lose that battle with gravity, and it's going to want to fall down into the chamber that we've created. So immediately around the chamber, it's going to fall in. Then whatever's above that, again, because of gravity, it's going to fall in, and so on and so forth. So you're going to get a cascading column of debris that's going to want to fill the void that you've created from your underground detonation. If you're close enough to the surface, that chain reaction is going to go all the way up to the surface, and you're going to have some of the surface material is going to go down to help fill in that hole that you've made. When this happens, we get basically the ground around the detonation site subsides or goes downward. And so they're called subsidence craters. And what we can see here is this happening, sort of a snapshot of seeing that moment when the material that we have at the surface collapses down and tries to help fill that hole. And so that's all that dust and stuff being kicked up by the movement of such a large volume of what is essentially dirt at the surface of the Nevada test site. Now here we can see at the Nevada test site an aerial view that shows a whole bunch of these subsidence craters. Now you can tell the difference between a crater that was made by the ground subsiding, or because it just filled in the hole that we created with an underground nuclear detonation, versus one that was created by a detonation that actually breached the surface, is the fact that there are no lips around these craters. In fact, they look very similar to a sinkhole. And if you think about it, a sinkhole is pretty much the same thing. It's where we create a void underneath the ground, and there's not enough structural support for whatever's above that void, and it just collapses in until either you run out of material or until it completely fills that hole. And that's what we see here. But there won't be any lip to it because we didn't throw anything out. So there was nothing that would fly out and then come down and build up around the rim of the hole, as you would see with a crater that was made by that very process where a bunch of stuff gets ejected. So again, that's the way you would tell these types of craters apart. If it's got a lip, it was created by something that actually breached the ground. If it has no lip, it's basically a sinkhole or a detonation that was contained, and we're just filling in the hole that it created. Speaking of holes that were created by stuff getting ejected, we have here, I think it's the largest crater we ever produced with a nuclear detonation. And it was from the Sedan shot nuclear test. It's called Sedan Crater. And I've got two different pictures here. One is sort of a viewing platform that's set up at the rim, one side of the rim of the crater, and then an aerial view. And so what you can see here is this little tiny spot right here, this little white dot. That is this viewing platform. So you can get a sense of scale to actually how big this crater is. Now, there's also a plaque right next to the viewing side, and that's this little thing right here. And what it's showing is the yield of the weapon. It was 104 kilotons. So when it happened, what they classified the soil was called alluvium. How deep was it buried? 635 feet. What was the size of the borehole that they lowered the weapon down into? It was only about 3 feet, so probably had really good coupling with the ground around it. And then the crater is 320 feet deep, but almost 1,300 feet in diameter. This is one large crater. Again, I think it's the largest that we ever produced. And then you can see some other statistics. The volume was 6.6 million cubic yards. And then the total weight of the material that was lifted up because of this detonation is a whopping 12 million tons. So if you had a hard time sort of getting an idea of how powerful nuclear detonations are, I mean, they're powerful enough to move 12 million tons of material in a single shot. And it's not even a super big detonation. It's only 100 kilotons. I say only 100 kilotons, but that's remembering that the largest nuclear weapon we ever had in our arsenal is 25 megatons. So yeah, a whole lot of power being produced in a very small amount of time, and this is what it can do. Now, to be a little bit more technical about it, let's look at these sets of diagrams. So very similar to what we saw, we have our growing initial cavity that we create when the weapon detonates. We create that high temperature, high pressure, ionization occurs, and then starts pushing outwards. Then we hit the melt stage, the fracture stage, the deformation stage, and so on and so forth. But initially, as this thing is starting to expand, once it stops that ionization and that pressure, just like it does with atmosphere, that pressure wave starts to expand. We have that P wave, or that primary pressure wave, and we see it right here. Now, if you're shallow enough, as it approaches the surface, it's basically pushing a whole bunch of material, and it's going to cause deformation of the ground. So it's going to bow outwards, if you will. Now, when it does this, it's basically compressing all of the air that's near it, right? So as your ground moves up, you're pushing air up with it. So in that way, you're transmitting that primary pressure wave, or that P wave, into the atmosphere and creating an overpressure wave, as you would do with an atmospheric detonation, just not nearly as intense. Depending on how much ground was moved and how fast it was moved to create that compression wave that then propagates through the atmosphere. Now, as this happens, so we're transmitting that primary wave up, okay? So we have basically the ground moving up, right? But then what we end up having is an area of low pressure, right? Because we just pushed all the air out of the way, which is going to create a downward traveling wave. But it's not a pressure wave. It's something called a tension wave. Just trust me, they're different. So we have our outward moving pressure wave that's now in the atmosphere, but we also have a downward moving tension wave. So that downward moving tension wave basically meets the continuously upward moving pressure wave from the detonation, and they slap together. And when this happens, basically the surface where this occurs at, we're hitting it with downward pressure, upward pressure at the same time, and you're kind of breaking up all of the material that's there at the surface. So if it was some kind of hard rock or conglomerate or something densely packed, holding itself together, this meeting of the tension wave and the primary pressure wave will just break it all apart, which helps for the next stage, which is all of the gases, and that heat and that pressure that we've produced from our nuclear detonation is going to want to try to get out, and it's going to move towards, it's mostly going to go up, because as you move up, you get, atmospheric pressure becomes lower, so high pressure area wants to move to low pressure area, and so it's going to severely distort the ground in a very short time scale before finally just completely pushing everything all the ground out of the way, making it all go airborne. So basically everything between the nuclear detonation and the surface of the Earth gets pushed upwards and outwards, or ejected from the now hole that we've just made. Something else occurs too, and I want to point this out, is so we have our primary pressure wave that we've created by the expansion of our nuclear detonation, and this travels through the Earth, and this can damage underground structures. But we have another type of pressure that's transmitted through the Earth, and it's something called air slap. Now, air slap occurs when we have this deformation of the Earth that interacts with the atmosphere and creates that outgoing pressure wave and that downgoing tension wave. Well, that outgoing pressure wave, as it expands and it interacts further away from the detonation point with the ground, it basically slaps the ground or pushes on the ground very, very rapidly. And this is something called air slap, because the air is slapping the ground and it's creating secondary pressure waves that can then they can travel through the ground. So you can get, say you have an underground facility or underground structure, it can get hit with the primary wave, but it can also get hit with this secondary pressure that is formed by the atmospheric pressure wave that we've made, slapping into the ground at some other point, so that you now have two different types of pressure waves that can converge onto a single target. So this is diagrams in your book, and this diagram has a ton of variables. It's got too many variables, in my opinion, for what we need. We only need 3 things off of here. We need this one, DOB, or depth of burst. We need DA, which is the apparent depth of the crater. That is, after everything is all said and done, how deep are we measuring the crater? And then we have RA, which is the apparent radius of the crater, again, after everything is said and done and everything has stopped flying around. The reason that they're apparent is because they're not the radius or the depth of the crater that was produced at the moment everything got shot out of the way of the detonation. Okay, this happens afterwards when all that stuff that got thrown up into the air comes back down. It's the sides of the initial crater not having the structural stability to hold themselves. Like, try to excavate a perfectly cylindrical section out of a sandbox. Well, you can scoop sand out from a given point, but you'll find that the walls will start collapsing and then filling that hole back in. That's exactly what happens with a nuclear detonation. So these are apparent because they're not what occurs right when that ejection of material occurs, but what happens after everything has fallen back in and the walls have semi-collapsed and filled back in. Also, we have on this diagram the area that they call fallback. This is what I've just described. This is material that has fallen back into the hole, either from the sides or rained down in it from all the stuff we shot up into the air. Then we have the rupture zone. This is that area. So we have the ionization, then we have melting, and then we have that high pressure, which is enough to fracture the rock or the material around the detonation point. And then finally, as we move out, it's not enough pressure to fracture the ground, but it is enough to sort of compress it and kind of move it a little bit, but it doesn't structurally significantly alter it. So the rupture zone is just what it sounds like. That's where we're fracturing all of the ground. And then we have the plastic zone, which is where we get the change in density, physical deformity. So we're pushing it out of the way, but it's in a plastic sense, which means it's still the same as it was before, just slightly more dense and now in a different place. Excuse me. Okay, more reference curves. We've seen these before. These are for figuring out what is the depth of our crater and what is the radius, apparent depth and apparent radius of our craters. Now, these are 1 kiloton standard. Hopefully by now you understand how to use these. The main difference is, unlike what we saw with atmospheric, where, let me get my thing here. In atmospheric, we scaled with yield to the 1/3. For underground, however, it's a little bit different. It's the yield to the 0.3. So we have to end up doing the same thing, which is, of course, scale in and scale out. But this time, again, it's 0.03 instead of 0.33. Not a huge difference. We have several different kinds of soil here. For both the the radius of the crater and the depth of the crater. You kind of just, whatever your depth of burst is, scale it, find out where it meets here on the axes, read off what it should be, and then, of course, we have to scale that back out. Okay, then finally we have this particular plot here, which is 4 different yields, 1 kiloton all the way up to 1 megaton. And this is from the Air Force Systems Command Manual. And basically what we're doing here is, you could draw a bunch of successive lines in order to interpolate for a yield that was different from these particular ones. You would find out what the range from the, I guess you could call it underground slant range, would probably be appropriate. Depending on the depth of where the burst was going to occur. And this isn't scaled, so you would simply find where your structure was located, draw the straight line, depending on the yield, and then figure out was there enough damage to an unlined or not reinforced underground structure, whether or not it was going to take any damage, or the threshold for damage to a, I guess you would call it a hardened underground target. And that's pretty much it for this one. A real simple way of finding out whether or not there would be some kind of damage, moderate, light, severe, which we can see on this last slide here, looking at table 6.108, and there's another table that's not just for structures, but for machinery and things of that nature. It's very similar to what we saw when talking about air blast. So in this particular case, for this one structural type, which you could think of as a reinforced structure, small, heavy, well-designed, reliable, this would be something like a nuclear bunker, if you will. So distance from surface 0, 1.25 apparent radii from that particular point would give you severe, and severe damage is listed here as being complete collapse, or light damage, which is about double that, which is where you get, again, the same thing as we saw with light damage to a surface structure, which is there will be something, but it'll be minor and repairable and not a huge issue. Now, relatively long structures, think things like pipelines or very long rooms, if you will. Because of their length, they will experience a pressure gradient, so that you'll have one part of it experiencing a much higher level of pressure than another. And in this particular case, you can see much more severe damage at further away. And severe damage here being deformation and rupture. Again, think kind of like a pipeline. So where you would see it actually get bent, and the pressure differential would cause cracking in it, and they're leaking and whatnot. So it would not be even remote to being straight anymore. So that's the severe deformation, and of course rupture would be splitting it open. Moderate damage would be a slight deformation, so it wouldn't bend it in a circle or something like that, but it would bend it enough to where it wouldn't be straight anymore. And again, you would have some rupturing, but not nearly as much as you would have in the case of severe. And then finally, with light damage, you really wouldn't do anything to the pipeline itself, but you would put a lot of stress on the joins of the pipeline where it was either welded together or bolted together, and those may fail under so-called light damage. So that's it for looking at underground detonations and what they produce and how does that affect things, specifically targets. Most underground structures that we would be concerned about with regards to a nuclear detonation, and an underground nuclear detonation, this day and age would fall under the category of something like a nuclear bunker buster, if you will. We had a project like that. It was called the Robust Nuclear Earth Penetrator, which ended up not going forward, but that's not to say it couldn't in the future. And this would be kind of the scenario. And in that particular event, you would be looking at intentionally hardened structures, silos, or bunkers for military or political leadership. This gives you an idea of what you could expect from something like that. And again, the previous plot with the different yields showing, how far away are they versus are they going to sustain some sort of damage, and then this table kind of delineates what that damage would be. In the next lecture, we're going to look at what occurs underwater, and very much like underground is very different from atmospheric effects. Water is even more different, and that has to do with the incompressibility of fluids and the ability for the pressures and the shock generated by a detonation to propagate very much further and still have damaging effects than we would see underground or even in the atmosphere.